Hello. You can use chat to ask questions if you have any. If you're still there. Where do you want to go over?
All of it.
All of it? Like just a general review of things? Or practice exam or what?
Not the exam.
Not the exam.
Unless you guys want to go to the exam.
Oh, I don't particularly like it.
Do we need to
Okay, so the exam is starting electric current, right?
Yes.
Okay. So do we want to try to go over one topic at a time? Yeah.
do Clay, you said Kirchhoff.
Hey,
You
what's
want to go over?
up?
Come on, front row
You
with
can
us.
sit up here if you want.
You know you want. Should we start with Kirchhoff's?
Kirchhoff's? Okay.
Yeah.
Before that, well, since the electric current, which is basically resistor simplification, comes first. Is there any questions on resistor simplification? Do we all know how to simplify resistors?
Yes.
Yes. Hopefully. Okay, let's do Kirch. Okay. Is the concept okay? Are you guys good with the concept?
Yeah.
You know what it means when you take a loop. And, okay. So how do you solve the equations in general? Is that the problem?
Personally, I think the problem for me is like, okay, you have a loop, but like when, I don't know, like when do you use certain loops, like with the opening and shutting thing, or like when is the, like, or like the switches, sorry. I don't
Oh,
think
that's
you
for
can
the capacitors.
Oh,
Yeah, that's one.
sorry, is that something completely different? Wow.
Yeah, that's the one that
This is
IRC with switches. Yeah, IRC circuits.
Okay, well, let's just
We'll get to that. So we'll just go over general. R2, R3, B3. Okay. So in a question like this, they would ask you to find the current through every loop. When you find the current through every loop, when you find all the currents in the circuit, you know everything about the circuit. They'll probably tell you in which directions the current, the assumption of the current is going. Actually, let's call this I1, this I2, and this I3. So this is just an assumption. It's not necessarily true that that's the actual direction. If we get a negative current for I1, for example, that means it's going in that direction instead of this direction. Okay, so we have 3 currents. That means we need, so 3 variables. For 3 variables, we need 3 equations. Our first equation comes from this loop. The second equation comes from this loop. And the third equation comes from this node. So KCL at the node gives us, so that's the sum of all the currents going in, should be equal to the sum of the currents going out. Currents going in is I2 is equal to the ones going out, I1 plus I3. For the loop equations, there are multiple conventions. I'm going to use the one that the professor uses. So for this one, there's like positive V1. We have a voltage gain. Across this resistor, because the current is going in this direction, that's also a voltage gain. Across this battery, there's a voltage drop. Across this resistor, there's also a voltage gain because we're going opposite direction of the current. R2, I2, is equal to 0. For this loop, we do the same thing. That's going to be minus 3, and because we're here, we're also going to lose I2, R2 is equal to 0. Does anyone have questions on these? How do we get that?
Wait, isn't it minus R2, I2 for the first one? Oh, just kidding, it's going the other direction.
Yeah.
Okay. Is that a negative I2 for Kirchhoff's law?
Which one?
It says a semicolon and then a dash. No, up.
It's the I2 equals I1 plus I3 up the first
Yeah.
equation.
It's
I2
not a
equals.
negative. No, before it, there's like a negative.
No, it's just
Okay.
Good.
Okay.
It's like a snotty face with a, yeah, it's
a
good.
mustache.
Great.
Okay. So any questions on how to get these equations? No? Okay. So how do we solve these equations?
Yeah, that's nasty.
Yeah,
Okay.
that's
We can, does everyone not have a calculator that can solve matrices?
Can we go? You're going to teach us how to do that? OMG.
You can teach us.
You have one.
I don't know how to do it.
Okay.
OMG.
Okay, so does anyone have a calculator that can solve matrices?
I have it.
Yes, at least that.
I have it, but don't know how. Just don't know how
I
to do it.
Okay. If you all have one, I'm not going to go over how to solve it with hand, because that's going to be a waste of time.
Good.
Okay. So, to solve it with a matrix. So how do we solve equations with matrices in general? You're going to have, so let's say, before we get to that.
Wait, I just have a really general question. It
Yes.
sounds really stupid though. So
Go
for
ahead.
Kirchhoff, you use both of them in every scenario, right? Like for the rules in general, when you have all this, like the setup, when you use both of the rules, right? Like I have a node, so I'll
Generally, for two loops, yes. You're going to have one for the node, one, two loops.
two loops.
For two loops, that's what.
If it's one, then you just use the one loop and then
One
whatever.
loop, yeah.
Like, no nodes.
You need as much equations as you have variables. You need three variables. You need
Okay.
distinct equations.
Okay.
So one equation has to have something to do with this loop. Another equation has to do something with this loop. And since you already use these two loops, you can't use a bigger loop because that's not a distinct equation.
Okay.
That's why you need to use this node here.
Thank you.
Okay. So for solving equations with matrices in general, let's say we have 1a plus 3b plus, actually let's just do a 2 by 2, equal to 5. And then you have 7a plus 8b is equal to 9. Okay? We can write these as a matrix with coefficients. This is a 1, 3, 7, 8. This is the matrix of variables, A, B.
Hey, Bizzle,
Yeah.
are you streaming right now?
What?
Are you streaming?
No.
Are you streaming?
Yes, what?
Okay, because I just had a friend who said that you weren't streaming, so I was wondering.
Should be. Yes. Share the whiteboard. Oh, that's not good. Can you see it now? Dom? Yes, okay.
Okay. So this is a multiplication. Matrix multiplication goes, so we multiply A times B, and gives you that. So this is your general form. If you have these equations, put them in a form of a matrix, this is how we do it. So now, back to our equations. Our variables are just I1, I2, and I3. I1, I2, and I3. All equations only have I1, I2, and I3 as variables. Everything else we're assuming is given by the question. So we have to arrange them in the form of I1, I2, I3. So in this case, it's going to be I1 plus I2, sorry, minus I2. We move them all to the same side. Plus I3 is equal to 0. We want to write all the equations in this form. Our 1 I1 plus R2 I2 plus 0 I3 is equal to, move the voltages to the other side. It's going to be V2 minus V1. This is your second equation. Same equation, we're just putting it in a different form. 0 I1 minus R I2 minus R2 is like, this is R2.
Yeah.
Oops, 2R2 minus R3 I3 is equal to V3 minus V2. Now you have your equations in this form. You write the matrix 1, minus 1, 1, the coefficients, R1, R2, 0, 0, minus R2, minus R3. This is the matrix that we don't really care about when you're using a calculator. So we're not really going to plug this in. Is equal to what we have. So this is going to be equal to what we have here, which is 0, V2 minus V1, V3 minus V2. Remember that all these variables, other than I1, I2, I3, are actually constants. We have them in the question. They're going to give us our 1s, V1s, V2s, and whatnot. So these are actually numbers that we can plug straight into the calculator. Okay. So, for example, you want to do a calculator with a calculator? Okay, can I use yours? Okay, so to do it with a calculator.
Which one?
It should be NTI.
Okay.
NTI should do the same thing. So if you go to second matrix, you have three choices. There are three tabs on the top. One that says names, math, edit. Go to edit. Select any matrix that you want to use.
Which one does matrix have?
X to negative 1. For this one, at least. Okay. Right there.
Oh, I agree.
Oh, he's got a higher power.
Every time I try to do a question, I'm like, you can take my right answer. I just physically cannot. There's nothing wrong.
Okay, I'll show you guys after class so don't waste time on this. But it's really easy. It just takes like 5 seconds to do it. I'll show you guys after class. Okay, assuming, I'm just going to go over how to solve it really quickly. Assuming you don't have a calculator, you don't know how to use it, so you forget to use it. So the way to solve these is you have two equations that have, so this equation has all the variables in it. This equation only has I1 and I2. This one only has I2 and I3, right? That means we want to eliminate the one that's not in common. This one is in both equations, right? That means we either want to eliminate I1 from this or I3 from this. If we eliminate I1, to eliminate I1, we just need to write this equation in terms of I1, solve for I1, plug this into I1 here. That's going to be R1 times this entire thing. Then write the coefficients separately. So this is going to be so R1 I2 minus I3 plus R2 I2 is equal to V2 minus V1, right? So now we don't have any I1 in our equations. We're only left with, so to simplify this, R1 I2 minus R1 I3 plus R2 I2 is equal to V2 minus V1. We can combine the R2s. Remember, these are numbers. It's just going to be R1 plus R2 times I2 minus R1 I3 is equal to V2 minus V1. Okay? The second equation that we didn't use is this one. Oops, sorry, it's this one. Minus R2 I2 minus R3 I3 is equal to also V2 minus V1. Oh, V3 minus V2. V3 minus V2. So these are just numbers, right? So if you have 3A plus 4B is equal to 6, 7A plus 8B is equal to 11. You want to solve this system of equations. What do? To eliminate A, all you have to do is multiply by negative 7 over 3. The entire equation, and add them together. Right? Mm-hmm. If you add them together, that's going to give you, nothing here, negative 7 over 3 times 4, B plus 8B equal to negative 7 times 6 over 3 plus 11. Okay. So the same logic here. With the same logic, you multiply by, in this case, you just multiply by R2 over R1 plus R2. This, when you add this to that, after you multiply, it cancels out, and you're only left with one variable, and you solve for that variable. Right? Okay.
Hopefully, you all have calculators, so you don't have to worry about this. Questions? Okay. So, any questions on that? No? Okay. This is basically all you have to do in this section. Know how to apply Kirchhoff's laws. Next one is capacitors, RLC circuits. Okay.
Okay, RLC circuits. Should we go over something?
Yeah, can we kind of go through the homework problems in this one if everyone else is up for
And the problems?
Yeah.
Let's do some problem with practice test. It's like 32 points.
Okay. All of them or hardest one? Which one?
Sure, let's do the hardest one.
I don't know which one is the hardest actually. This one looks like it may be hard.
This one was like the which problem that we did in class.
Yeah. So let's not do it.
Whiteboard
Is that what you're saying?
if you don't mind. Thanks.
Here, did you see this one?
Whatever, really, they're all saved, solved in a similar way. Okay. R1, R2, R3, B. What can they ask about this? Current in a particular part of the circuit after you open the switch, after you close the switch, and so on. So there are two states. The capacitor is either charging or the capacitor is discharging. If the capacitor is discharging, obviously it means that it has already charged, right? So that's going to happen when you close the switch. The capacitor is going to start charging, right? The charge on the capacitor looks something like this. It's 1 minus e to the negative t over tau. When it's completely charged, that's when you open the switch. When you open the switch, it's going to start discharging. It looks something like that. So that's the charge on the capacitor after 40 volts. Yeah. Okay, so they usually ask not in times, I mean, most of the homework problems, I don't know if they ask you anything in t equals 2.7 or something. Did they ask something like that? No?
No, it's always
Only at start and end? Okay.
Yeah.
So we'll just do that. So at t equals 0, when you close the switch, right when you close the switch, what's going to happen? Close the switch.
There's going to be current going through everything.
What's that?
There's going to be current going through both.
Yes, there's going to be current going through both. What's going to happen to the capacitor?
The excited wire.
It's going to be like a wire, right? It's going to look like a wire. Therefore, if they ask for this current, for example, how do we find that current?
Do the voltage divided by the total resistance and get the overall current, and then
We can do that. So one way to do it is to simplify the resistors. Let's take values for these. Easy, like
1, 2. 4 and 6.
1 to 4, 1 to 3 is 4. So 4 and 12. So that simplifies it. These would be 3, 6 ohms. 6 ohms is 9 volts. Okay? That's a 12. Alright, so at time t equals 0, the capacitor does nothing, right? Because it's still completely uncharged. It's going to let as much current as it comes in it go through it, right? It's an open circuit. So if it makes your life easier, you may want to draw the circuit at every stage, just to model what the capacitor is actually doing. Here we model this as a wire because it's acting like a wire. We have 4 and 12, and we said this is 6, and this is 9, right?
Yes.
4 and 12 in parallel, it's going to be equal to 1, 2, 3, 4, 12. It's equal to 3 ohms, right? So this can be simplified into a 4 in parallel with a 12. It's equal to 3. You can do the math. Find out that it's 3 ohms. So you're going to be left with a resistor, 3 ohms. After you combine them together, 6 ohms, 9 volts, right? Remember, we were trying to find the current through one of these branches. Doesn't matter. So the voltage across each branch, since we have 9 volts here, we have 9 volts in total. It's going to be 3 volts here, and we're going to have 6 volts across this branch, right? Should I slow down?
Would you just draw?
What's the voltage across each resistor?
Oh, okay.
3 volts here, right? If you want to, one way to do that is find the current. Let's call it I, big I. Big I is equal to 9 volts over 6 plus 3, which is equal to 1 amps. So the voltage across this resistor is going to be 3 times 1, which is equal to 3 volts. That's the voltage here, 3 volts, right? That means the voltage across here is also 3 volts, plus minus 3 volts. So to find the current across one of them, E is equal to IR. This is the current through the resistor. Current through the resistor I is going to be equal to V over R, which is V over 12. If you want the current through this, it's going to be 3 over 4. Okay? Okay? Okay. Right. So now they may ask something before we erase this. Now they're going to tell you what's going to be the current. Actually, we can erase this. What's going to be the current that's running through the 4 ohm resistor after a really long time from closing the switch? So now we close the switch a really long time. What's going to be the current that's flowing through this resistor? How do we find that? What does the capacitor look like after a long time?
It will just be going to the first loop.
Right. So the capacitor is
Fully charged.
no, it's fully charged, right? So fully charged, so it doesn't look current through it. So it's open circuit.
Yeah, open circuit, that's fine.
So you can just redraw the entire circuit. Open circuit. If a loop is not closed, there's no current flowing through it. There is no current here. I is equal to 0. Right? Right? Okay. So if you want to find the current here, that's just going to be are these two in series or parallel? Series, right? Series because we have the same current flowing through them. 6 plus 4 is equal to 10 ohms. 9, which is a voltage, over 10 is equal to 0.9 amps. So you have 0.9 amps flowing through this branch. 0.9 here. Right? Okay. Any questions? Am I going too fast?
Can you slow down?
Yes? Someone say yes?
No questions.
No questions, okay. Now, if we open the switch, what's going to happen?
It's gonna go in the second.
It's going to start to discharge. Okay, so we open the switch. What happens to this circuit? Is there any current flowing through here?
No.
No, there's no current here. I is equal to 0. That means there's only going to be current in this loop. What's the direction of the current?
Opposite.
Like that, right? Because originally the capacitor charge would be positive and negative, and now it's basically like a battery. Think about the capacitor as a battery. Battery that's discharging, positive and negative. Therefore, it's going to push current in that direction, right? Okay. So to find the current that the capacitor is outputting, it's called as IC infinity, or IC 0, right, through the capacitor at time 0 after opening. To find IC 0, we're going to have to know the voltage of the capacitor. How do we find the voltage of the capacitor? Remember this picture that I drew. Starts charging. Here's where you change the position of the switch. So here's where you close the switch, or open the switch, sorry. Right? This is Q. So it starts charging, and it starts to discharge. Q is equal to CV. That means the graph of V is the same thing, V. But, multiplied by a constant, more or less. So the scale is going to be different. That means V is the only thing that stays the same before and after you open the switch. So the voltage on the capacitor is going to be the same, right? So if you know the voltage before you open the switch, you're going to know it after you open the switch. So the main thing to find out is the voltage across the capacitor. Okay? So to find the voltage across the capacitor before you open the switch, so in this situation, right? Here's the open circuited capacitor here. What's the voltage across this capacitor? This is before we open the switch. What's the voltage across it? How do we find it?
I have no idea. Oh, it's the same voltage that's going down the other branch.
Same voltage across this branch.
Yeah.
What's the voltage across this resistor?
3.
Why?
That's 3
Why?
volts.
Is there any current running through this resistor? I is equal to 0. Why is there a voltage across a resistor that has some current flowing through it?
Why is I equal 0?
Because the capacitor's been charging for quite a while now. So it's completely charged. So the current through it is 0.
So there's no voltage?
There's no voltage across this resistor, right? But this branch is still connected in parallel to this, right? When two things are in parallel, their voltage has to be the same. So the voltage across here has to be the same as voltage across here. There's no voltage across here.
And the voltage across the middle one is 3, right?
So it's plus minus 0, plus minus VC, right? This is plus minus, let's call it V4. V4 has to be the same as VC plus 0, right? So VC plus 0 is equal to V4. That means V4 has to be equal to VC. We already found, we found the current that's going through the 4-ohm resistor. So VC is equal to the current that's going through the resistor, which is 0.9, times the resistance V equals IR Ohm's law 4, right? Which is equal to 3.6 volts. So there's basically 3 states that they ask about. First one is right when you close the switch. Right when you close the switch, the capacitor is completely uncharged, therefore it's just a wire. We ignore it, we just connect its terminals and act like it's a wire. The second one, the capacitor is just open circuited. You just take out the entire branch that has a capacitor. There's no current flowing through that branch. But in this second state, this is where you find the voltage of the capacitor to move it on to the next state, because it stays the same. Right? So when they ask you about the voltage right after you open the switch, you have to know the voltage right before you open the switch. So we just found out the voltage right before we opened the switch is 3.6, right? So now the circuit, we're ignoring this part of the circuit, and we have a capacitor here. That's right after. And we have some circuit here that we don't care about because there's no current flowing through it. Well, this resistor wasn't here. Well, it's the same thing, but it's 12 ohms, and this is 4 ohms. And we want to find the current across the 4 ohm resistor. Current's simply going to be 3.6 over the combination of resistors, 4.12. 3.6 over 16. Whatever that gets you.
What is that?
That's the current through the resistor.
Which one?
Okay.
Yeah. It's the same current, right?
What's VC?
VC is the voltage across the capacitor.
Oh,
Yeah. VC is the voltage across the capacitor right before you open the switch and right after you open the switch.
What's the question?
I didn't ask.
So
Wait, scroll.
right now,
if someone to ask a
the
question,
equation,
I feel like
What is
something
V for?
the equation we use right now is V equals I times R.
V equals IR, most basic one electricity.
Yeah,
Ohm's law.
but we didn't use Q equals CV.
We don't need to do
Yeah,
that. If they ask you to find the charge on the capacitor right after you pull the switch, or right after you open the switch or something,
Then
from the voltage you find the charge.
okay.
Right? You don't know, so the circuit itself doesn't really tell you anything about charge. You need to know the voltage and the capacitance to find the charge. So if they ask you what's the charge on the capacitor right before you open the switch,
What's 0.9?
What?
What is 0.9?
0.9 was the current that's flowing through this resistor,
Through which one?
through this resistor, or through this resistor, or through this battery. Right after a really long time, it closing the switch. Because after a long time the capacitor is open circuited, right?
So then the other I is through the capacitor?
The other eye is when you open the switch.
Oh.
When you open the switch, the capacitor is going to start to start it.
Where did 9 come from?
Where did 9 come from? It's voltage.
Yeah.
That's the battery. So I mean, at any moment, if they ask you to find the charge, at any moment, as long as you know the voltage across the capacitor, you know the charge, right? Because Q is equal to CB. You know the voltage, you know the charge. Right? The voltage of the capacitor you don't find directly. You find it based on the elements that's connected to it.
So the 3.6 over 16 is the current for the entire circuit when it's open?
When it's open.
After it's charged.
Yeah, after it's charged. Now it's discharging. Yeah. And there's no current through the branch that has a battery in it, right? Because the switch is open. So there's no full loop. Current only flows in a full loop. Any questions on this?
I have a question. This from. So for this one, it asks like when the switch is first closed. At the instant it's closed, what is going to be the current? So then again, the capacitor acts as a wire, but it only uses R1 and R4 to find the current and not R2 and R3. Is that because originally, like when a capacitor it only goes through this original loop, and then it goes through this one.
Since the capacitor is a wire,
It was like the shorter route.
yes, it's the least resistance path. I mean, the path of least resistance. It's the same thing. It's basically the same thing.
Mhm.
So, and this is the switch. And we want to find the current through the circuit, this current I, right when we close the switch. What's going to happen to the capacitor right when we close the switch?
So I'm trying to-
It's going to be a short, right?
Yeah.
So, capacitor is going to look like this. And which resistors do we use to find the current?
R1.
R1. So V is equal to, that's right,
Oh, I is the voltage of the battery over the resistance of one,
R1. Why do we not care about R2?
because it's gonna fill this one
Because
first.
there's no current going through R2, right?
Yeah.
Because remember that the voltage across the wire,
The voltage drop across the wire, assuming it's going to be zero, assuming ideal wire. So the voltage drop across the wire has to be zero. That means the voltage drop across the resistor is zero, because they're in parallel. Since V equals IR, V is zero, R is not zero, and I has to be zero, right? This is zero, I has to be zero.
that's why there's no current here, and all the current just goes through this one. Okay.
Wait, this one's for when it's closed at T equals 0?
Yes. There we go.
So even though it's a wire, there won't be any current going through the other resistor.
Even though it's a wire?
Even though the capacitor becomes a wire.
Yeah. So the capacitor the capacitor was here,
Yeah.
okay? And when we close it, the capacitor is going to be a wire. So since it's a wire, the resistance of the wire is way lower than the other resistance, so all the current's going to go through it.
Does that go for all RC circuits, or should I take another example? Huh? Another example? Okay.
Can you do the one from the practice exam? Can we do the one from the practice exam?
Don't try to confuse
Okay. Switching the circuit board has been open for a very long time. G1, R1. Okay. R1. 38 ohms. R2, actually, let's put out R1 and R2. 38 ohms. Well, there's another one here. 38 ohms. Card 2 is 50. 2 ohms. R4, R3, and R5 are 38. 38. And V is equals 1 volts. Switches are closed, blah, 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 blah. Okay, so they do ask whether the time constant of the circuit is 1.5, how much of the maximum current will remain? After 6 seconds, you actually don't need to calculate it. Now we open the switch. Do we have the capacitance? No, and that's part of telling you the time constant. Okay, so they ask, this is a good question actually. What is the current that passes through R2? Yes, we should let R2 is this one.
What is the current that passes through R2 right after the switch is closed?
I'd say 0.
0.
Where's
Right.
the switch?
Good.
Switch is here. Why is it R2? Why is it 0?
Because of the capacity.
Because of the capacitor, right?
Wait, the question. Repeat the question. I'm sorry.
What is the current that's passing through the resistor R2 right after you close the switch?
It's only the first.
Right. It's 0.
Why?
Because the capacitor is much lower than R2.
Because right after you close the switch, the capacitor is basically short-circuited, right?
It's excellent.
That what? Okay, so, no, wait. So, the current in any circuit, the current is going to always take the path of least resistance. Okay? So in terms of this, so remember his analogy, his current analogy, that when you're going through a sidewalk or something, you're late to class and there's a lot of people in front of you. One path has a lot of people in front of you and the other path has no one. You take the path that has no one because it's faster for you. Current behaves the same way. Electrons think the same way. They always want to go where they want as fast as possible. The least resistance path is this one. So you want to take the least resistance. Always, okay?
So there's no current in the other two.
So there's no current in the other two, right? If there was a 1 ohm resistor here and 1,000 ohm resistor here, there's still going to be current that's flowing through here, but it's going to be really, really, really small. Right? It's going to be really small. So, I mean, you can find the ratio of the currents. The ratio of the currents that it's going to be the ratio I is going to be 1. Actually, I is going to be, this is 1 over 1,001. That's going to be really small compared to the current that's flowing here. In case of a circuit where you have no resistor at all, this is going to be, let's leave it 1,000, this is going to be 0 ohms, right? So the current that's flowing through here is going to be 1,000 over 1,000 plus 0, which is equal to 1,000. That's going to be a fraction of I total. So that's going to be 1,000. That's 1.
Yeah. Okay.
1 I total, which is I total. So all of I total is flowing here. It means 0 I totals. None of it. Always. A capacitor, anything in parallel with a wire, no current through that thing. Always. Okay? Sure. Great. Okay.
Wait, what was the question exactly?
So the first question was to find the current through R2.
Okay.
What is the current through R2? Right. When you close the switch, right after you close the switch. Second question is, what is the current through R6 right after the switch is closed? Yes, I have to tell you. R6. What is the current through R6 right after the switch is closed? How do we find it?
Pay attention to the first.
So the current is only flowing here, right?
Yes.
That means 1 over 2 times 38. 1 over 38 plus 38 is equal to whatever that is.
Maybe 2 or 2.
2 times 38, or 38 plus 38.
No.
38 to 38.
It's 1.
And the voltage is 1. Oh,
Okay. Not bad.
38 plus 38. Now, if we open up the switch after it was closed a long time, and we know that the time constant of the circuit is 1.5 seconds. So now, if we close the switch, capacitor charged completely. Capacitor was here. Capacitor is completely charged. Okay? And we know that the time constant, remember this guy, tau? Tau is equal to 1.5 seconds. That's pretty good tau. How much of the maximum current will remain after 6 seconds?
what do we do?
Uh,
How much of the maximum current?
solve for the capacitance first.
We can solve for the capacitance, right? We can do that. What's an easier way?
Was it easier?
What is tau? What is tau about the circuit?
RC.
Right. I mean, equation-wise, tau is equal to RC.
Tell me how long it takes
Tau tells you how long it takes to.
to charge it.
Right, but exactly
63%.
63%. So after that's 63% of 37% of discharging, and 63% of charging, right?
Yeah.
So if you're charging, this is tau. It's going to be 63%. If this is I max, this is going to be 63% of I. Okay. If you're discharging, it's going to be 37% of I. If this is your I. This is I max.
So if you lose, you lose that 7% of 1 volt and 1.5 seconds. So you lose that 7% of the original being 1.5.
It's going to be 37% of the original.
So you're losing 60.
At tau. You're losing 63% here. And you're losing, you're gaining 63% here. Okay? So at this level, you're going to be 37% of the original. Right? So you can either do it this easy way, which is at each tau, you're going to lose 37%. And he tells you tau is equal to 1.5 seconds. Already. And we want to find it at 6 seconds. 4 taus. So it's going to be 37% times 0.37 times 0.37 times 0.37 times 0.37 times. He wants how much of the maximum current will remain. So just a ratio. Or you can go about and find RC. It's going to be the same thing. If you go about and find RC, do you have to find C? You don't have to find C. You also don't have to find C if you want to do it another way. Just do it another way, just in case you can think of that. So let's say we want to do it. We want to find. Okay. So to find after we open the switch, I at any time t is equal to I max times e to the negative t over tau, right? As we discharge them. Looks like that. Okay, so we want to find I of 6. We need I max. When is current maximum? When is I max? When is I max? After you open it, right?
Yeah.
Okay.
Which is 1/38 times 2, right?
That's a voltage.
And then you multiply by
No, sorry, that's a current through this. We need to find a voltage across the capacitor.
Right, but that's I max. Right.
times I. Yeah.
That's not I max. That's voltage. So remember that the voltage
And this is
before you open the switch is the same as the voltage after you open the switch. And we want to find the current after you open the switch, which is going to be the voltage after you open the switch divided by the resistance. So let's first find the voltage across the capacitor after you open the switch. So we first charge it for a long time. When you charge for a long time, this is going to be an open circuit, right? This is open circuit. That means all the current is going here, right? Easiest thing to do is to simplify this branch, which is going to be 38 over 3. 38 over 3. 12.6. So you're going to have this 12.6, hopefully. This is going to be 52 ohms. Get to this, get back to this. And you have this resistor here, it's 38 also. You also have this resistor here that's V8. Okay? And we want to find the voltage from A to B, which is the same as the voltage of the capacitor, right? Because the voltage of the capacitor here is the same as this voltage or the same as this voltage, right? So we can find it any way we want. We can either find it as a voltage across this resistor plus this resistor, or the voltage across this resistor and this battery. Right? No? Why? Okay. What's the voltage across this resistor? If this is 5 and this is 3. What's the voltage across the resistor? 5. Why? Is there any voltage loss across the wire?
No.
What's the voltage from A to B? 5. This is 2 ohms, this is 3 ohms, this is 5 ohms. What's the voltage from A to B? 3. It's the same as the voltage across this resistor, right? What's the voltage across C to D? 2 volts. We can go as much as we want. We can say that so we said this voltage is 3, right? This voltage is 3. It was this voltage is 3. Voltage of this resistor plus this resistor has to be 3. And this voltage across this is 1 volt.
Why is the voltage across that 3 ohm resistor 3?
So you can do it the long way. 5 over, assuming we don't have this. 5 over 3 plus 2, actually that's not going to be 1 volt. It's wrong because it's going to be affected. We can do 5 over 3 plus 2, which is equal to 1 amps. That's the current, right? And V equals IR gives you V equals 1 times 3, which is equal to 3 volts. Right? Voltage division. We're using the same thing here. Voltage from here to here is the same as, it's the same in any way we take it. If we go this path or we go this path. This is basically the application of KVL. When you take a loop in KVL, you say that the changes of voltage has to be 0. That means halfway across the loop, if you go from here to here or you go from here to here, you're going to get similar voltages. There's no other way for it to drop to 0. Right? You gain 5 here. If you go here and you get plus 5, and you go this way, you get plus 5. That's the only way for it to be. So that when you go from here to here, you get 5 minus 5, which is equal to 0. There's no other way. Okay.
Can you scroll up?
Yes.
Oh, right there.
So the voltage across the capacitor, which is from A to B, is the same as the voltage across these two resistors. You can combine them. If you can't see it, we'll just combine them. That's going to be 64.6. When we combine the two in series, we just combine the two.
12.6.
12.6 plus
What did you get?
52.
You combined the other two.
We combine the other two.
Oh, and
38, 38 and these.
All of those.
Yeah.
Okay.
38 and 38 series.
Parallel 38.
Well, this 38 and this 38 series.
Oh.
And these are in parallel. It should give you
Oh, you're right. Yep, you're right.
1, 2,
Okay, scroll
2,
down.
3. Should give you that.
Okay. So then you combine those two.
What the? 64.6. What?
Yeah, 64.6. 6 repeating, but
And that's a squiggle. Okay.
Hmm?
That's just a squiggle.
but that should be ohms.
Okay.
Squiggle. Okay, so now we know that the voltage across the capacitor is the same as the voltage across the 64 ohm resistor, right? And we find that voltage by first finding the current. We don't care about this anymore. This is 1 volt. So the current that's passing through here is going to be 1 over 38 plus 64.6 plus 38. Yes, 38.
Didn't see.
You say you can hear some. I'm not confused.
Yeah.
So you get a value for I, okay? So that's going to be I over 64, which is the same as the current through all of them. And then to find voltage, V is equal to that current inside this current, 64 times 64.6.
Did you, that I-64?
This is the current through the 64 ohm resistor, right? Which is this voltage divided by total resistance.
Okay.
And when we find that current, we can find the voltage across the capacitor, right? Remember, the capacitor should be connected across here. So its voltage is the same as the voltage of this resistor. That's what we're trying to find. So this is also DC. Now, when you open the switch, there's no reason not to keep the switch and keep this entire circuit like this. There's no reason to go back to this original one. There's none at all, unless they ask for something there. So now, when you open the switch, we don't care about this entire part. This entire thing goes away. Now we have a capacitor here that's starting to discharge. It's going to discharge in this direction, right? And then we can find I max. Right? So then we can find I of t is equal to I max. Just found I max. E to the negative t over tau, neo tau. And they want it at 6 seconds. Find it at 6 seconds.
So for the IMAX, do we plug in I-64?
No, that's a current through this capacitor when you're after you charge it. Okay.
It's kind of crazy.
Okay. Okay, I'll come back to RC circuits at the end, since none of you like it.
We don't like much of it.
Yeah.
Well, I can't do anything about that, really.
Really just a whole.
Okay, I'll explain everything about RC circuits, starting
When
from
you-
Ohm's law.
When you
At the end.
calculated that third loop, you got 12.6, right? Isn't it just like, because you do series combination first and then parallel?
Series and series, 38 and 38 are in series,
Yeah, so
which
that's
gives you
76.
76.
And then you just do 1 over
76 in parallel with 38.
Yeah, so you do 1
Is it
over
wrong?
6. Yeah, it was 100. I got 100.
1 to 2 to 3. It should be. It should be 76 over 3.
Yes.
76 over 3.
25.3.
So that times 2. It should be 12. 12.6 times 2.
Okay,
Just a numerical.
that's where I was kind of confused.
Okay, I'll take another example on this later, but let's move on to something else. Magnetism. What's next anyway? Magnetism. Magnetism. Okay. This one is the F is equal to QVB.
How long is your session?
As long as it needs to.
What?
What? As long as it needs to. If I mean, you don't feel. What?
That's good.
Is that good or bad?
That's good. I think it's pretty good. As long as you need to.
I'm not trying to kick you off, but don't feel obligated to say. I know a lot of people have felt obligated to say in the past.
Well, theoretically, like, I'm only here for one thing.
That is.
Oh, but
So my homework,
Okay.
and I got lost when it came to ampere law.
okay.
So like, if theoretically, I'm only here for one thing, give me like a time frame that because I'm not trying to diss you enough, but I think you're an innocent guy. Like, don't get me wrong, but I'm not trying to be your own day.
Well, what's the question?
It's homework. Like,
I'm getting it.
It's very
You all the time as a professor and no one calls on him. He goes like, team with me, like every 5 minutes.
He's in a different class.
Oh, Lord. Okay.
Making sure.
That's
Stop now.
Okay, magnetism. A magnetic charge. This is the magnetic charge one that's moving in a. What's up? Oh yeah. Sorry. This is the charged particle moving field. Should we go over something here?
Yes.
Yes. Everything. What?
What's going on?
This section, charged particle moving in a magnetic field.
Wait,
Yes.
circular.
This circle.
Is it like that? Like,
In general, this is going to be something like you have a magnetic field oriented either inside or outside. Let's take something like this. You have a charged particle.
Fantastic. So
Q is equal to negative 30 microcoulombs. Okay, it starts out. Let's call this 0 point. Okay, and this is our imaginary y-axis. This is our x-axis, and the magnetic field is between. Well, whatever. It's negative d.
okay, because this practice is
And we can ask something like, where will this charge exit? And we know its velocity. Let's say v is equal to 5 Tesla. Velocity v is equal to 3 meters per second. And we want to ask.
C is equal to 5.
I'll just take this. Very good.
No, B is 5.
You feel
And it's coming into the board.
So we want to. They ask us something like, what is the radius? Or where will this
Oh,
charge
mass.
exit?
Mass is 0.1.
Mass is equal to 0.1 grams. Where will this charge exit?
I don't know. Okay, wait.
The radius is mv divided by qb.
So what's the direction of the force on it?
It's right here, cool, dude.
What's the direction? What's the direction of the
You don't want
force?
to know what I got.
What's the direction of the force on this charge?
Okay, have this I'll cross the years.
qb corresponds.
Oh, that's a wire.
Ice cream.
Sorry. OMG.
What's the question being asked right now?
Where does this charge exit, for example? Like, I can ask you anything.
So your fingers go.
So what's the direction on the force first? What's the direction on the force?
Feel
It's going
thumb,
this way, right?
Right.
and
Why?
it's gonna be this
Because use
rotation.
the right
This
hand
is
rule.
negative.
So.
Negatively charged, right?
Okay.
So you take the right hand rule and then reverse it. F is equal to QB cross B, right?
So it's gonna go.
B
I'm so sorry.
cross B gives you that direction if it was positive.
Wait, explain that again?
Which one?
Where you started using
That is so hard.
Well, this is the one I
Okay, don't give
finished.
up though.
When you have A cross B, gives you C. A is your thumb. B, A cross B gives you C. So in this case, it's QB cross B. B cross B gives you F. Because F is equal to QB cross B. Or you can curl your fingers.
Yeah, can you go over that? Wait.
Do that.
Oh, okay.
X is into the board, right?
X.
So
So you're into the board.
B-
E is into the board.
D cross B gives you F.
So it's negative.
You see,
Switch
That's negative. You're
Yeah.
Cross
makes
into
sense.
current. Or charge, fine. Okay.
Oh, I guess I was doing it.
right. If it was positive, it would be in this direction. But it's negative, so it's not that direction. That means the force would be that direction.
Negative. I'm just, wait, what's negative?
Q is
Sorry.
negative.
Yeah.
But
That's why
doesn't
you
Q
flip.
negative go this way though?
No.
Q positive goes based on the right hand rule.
Yeah.
So you have to reverse.
So it'd be like
Negative
this.
goes based on
Q, then you curl towards B,
Q, that's the direction that Q's going.
yeah. Then you curl towards B, and you force vector this way, to the left. Since it is negative, you switch it.
Oh.
So it's to the right.
Oh, because you guessed, like, oh, okay, well, oh, you
Yeah.
Okay, is it kind of like the current thing, but from before, like, oh, if it's negative, it shouldn't be negative, so flip to positive. Yeah.
You just need a way that works.
Don't know. It is not understood.
So
Claire, I know what you're talking about. Kind of, but not.
Is it, are you talking about like that one problem class?
No,
Like,
like,
it's when you're saying like the electrons are going counter, right? But current is actually down. It's not.
I don't think I was paying
but
attention.
I
So
like
it
it's something.
still is like.
I just-
Okay,
I'm just-
so electrons is negative. If it's negatively charged, it's negative. The direct, I mean, negative of the right hand rule.
So wait, just, I'm sorry, I'm so sorry. Try to explain one more time why it's going, why you flip it. I so get why it's going this way.
Negative because it's a negative. Yeah. So the right hand rule, they define the right hand rule if it was positive. I don't know.
Okay,
Okay.
okay. And then just
If it's negative
automatically.
charge, it has to move the opposite way. It's a positive
Yeah.
charge because
Okay.
it's negative.
You know how much
Okay.
poison you probably.
So we just reverse. That's a good convention.
because yeah,
Positive thing.
Hot water.
What's
Yeah.
it?
And because I probably squished it too.
Plastic like that.
This direction. That's it.
Right, it'll be okay. It wasn't winning.
Because you just multiply.
Yeah, good question.
Doesn't have
I didn't get it.
So positive force
trying to
right
do
here.
If you look at it that way, then you.
one of the things they can ask you is what's the radius? Yeah, or in what radius is going to go in? Okay. How do we find the radius?
MB divided by QB.
Wow.
Six,
Snaps and
MB
claps
over
for Aaron, everyone.
QB.
Aaron's gonna ace this.
It's not P, you just
I
take
don't know
the test.
about that.
We have M, we have B,
How much?
we have Q, we have D.
Take my
We find
I go
everything,
to a
right?
small school.
like 500.
You'll know.
So it's going to go like that, right?
Go to the auditorium.
Like that, with a radius of R.
That, I don't think I got it.
Wait, where is R coming in?
R is the radius of goes in, which is R is equal to MB over 3B.
That's right. R is N B.
Over 2B.
Crazy.
Are you gonna?
Crazy.
Is that standard?
Yes, it is. No, R,
Wait, what
MB,
is-
Q over B is from the
It's
left.
the
It's radius equals MB over B. It's from motion, U from B.
Is that like
I asked how much she said.
R equals MB, QB. It's on the motion.
Okay, hit me up.
But it's just, okay, it's just confusing. They're like, oh, is it resistance or oh, is it,
What's up?
Oh, it's just like R. Like
yeah, just R in general.
What's the check?
That we know it. We know
Oh.
everything. We know all of these. They're given. So we can find R.
Okay, wait, I'm just, okay.
And this is the
Let me get my
radius
brain out of
of.
this for a second.
This is the radius of the curvature. This is the radius of the curve that it's going to take.
Yeah, great, thanks. If you want a different curve, that'd be fantastic. Thank you.
So everything, yeah.
So, right?
Don't give up yet, CJ.
Okay, so we can ask something like this. Let's say we have a radius, the given radius of curvature and everything, okay? And we want to do something to the velocity to make the radius bigger.
You have to slow down the velocity to make the radius bigger. Right. If you speed it up, it'll be
Shorter radius.
So stuff like this, you might ask, bigger radius, what does it do? Smaller charge, what does it
No,
do?
but see, that's like 20 points, and it seems way too easy for 20 points.
All of this is sweet.
Hey.
Okay. Well, we'll do this. An electron moves from point A towards point B.
no one.
C.
Always get killed.
Yeah, I agree. So, no, that's the thing. Some of them you have to right.
Oh,
What is the general electromagnetic force on the electron? Assuming the distance between A and B is 4.15.
Which
The momentum of the electron is, okay,
Is this the question?
what do you use for momentum?
Yeah, it's in the
E,
parentheses.
M,
Which one? The one without solution.
Strength of the B field. B is equal to 3.2 milliteslas.
is that P?
P is momentum. What is momentum? MV. So in your equation, R is equal to MV over QB. P over QB. That's made it easier for you.
Wait.
What a gift! I feel so blessed.
Draw the approximate path taken. Okay, let's start by drawing the approximate path taken. There's an electron here that's going towards C.
It is. Okay, so that's the direction of
The uniform magnetic field is
it's going into the board. So let's find the first one. It's going into the board, and it's going toward
So what's the direction of the magnetic field?
a magnet.
Oh wait, is E coming from
So the
A?
electron starts at A and it's initially going towards C.
So that's that. So it's going through fingers forward.
So its velocity is initially directed towards C. And it's an electron.
Is that MT? 3.2 MT?
Millitesla.
What?
Wait, what are we finding? B field?
No, magnetic field. Yeah, B field. So magnetic field.
Force.
Okay.
Okay, so fingers go with
So it's-
and then
Yeah.
curl toward the
They
charge.
say the first question is direction.
So it goes
Yeah,
like
that's the
this.
first-
So it's
that's
negative,
the
so it flips this way. Is this
What's the direction of the
is
force?
it this way?
I assume it's like.
So B is that, right?
Yes.
B is in this direction. So sorry, we'll do the curve. B is in that direction. B is in this direction. So originally it should be like that. But it's
Wait.
negative.
What?
It's negative. So it's
You
opposite.
just said V's in the same.
B is in this direction.
But you point your fingers in the direction of V. Then
V
you
cross
cross
B
toward B,
gives you the
and
thing.
then it's force.
Ah.
Fingers into
V cross B gives you F.
so this is
If it was positive,
If
we did
but it's
wrong.
negative.
I'm gonna draw
It's
that.
negative, so it goes in this direction.
negative because it's an
That's the direction of the force. So the path it's going to take is going to look something like that.
You said negative because it's an electron.
Yeah. This is
Okay.
So that's
Wait, fingers.
so fingers move.
I should get one right here. Okay, what is the general direction of the magnetic force on the electron? Draw the approximate. You don't even have to do calculations.
Originally.
It moves from point A towards point C. What is the general direction of the magnetic force on the electron?
Okay, if it just like if
And then draw the approximate.
yeah.
Okay, let's say he asks for the
Okay,
radius.
so like how would you write that word? It's just like I don't know.
If he asks to find the force, how do we find the force?
Force equals
It's just plugging in. And mass, with the mass is not given, so we can't ask anything about the radius in this situation. We don't know the mass of the electron.
Warming.
Oh, it's given. No, the momentum is given, sorry. Oh, no, no. Momentum and velocity is given.
Can we calculate mass?
Oh, we can't find F because we don't know
F
mass.
equals QV.
But we can because F equals mass times acceleration.
Why were we crossing that?
Acceleration is v squared or r.
It's F
I
is
think we
equal
can
to
solve for it.
B cross B. But in this case, they're 90 degrees apart. So the cross gives you sine of 90, which is 1 to 1. Because V and B is in this plane, B is in this plane. So that's 90 degrees, however you orient it.
So it changes?
Changes?
Like, so you can't use QEV for everything.
You can't use QVB for everything. It's QV cross B. But in most of these questions, one of them is going to be moving in this plane, and the magnetic field is probably going to be going in this route. So that's
90
So
degrees.
just plug in value.
Mostly, yes.
okay.
But you would be able to solve
You
for mass.
can't just say it like that.
The half of that curve.
Then you're writing.
Yeah, that's a path.
So for question 1, would you just say it's going towards beta? Like fill in that blank? Going
No.
I'm
towards
looking at the next.
So what is the general direction of the magnetic force on the electron? It's going to be towards something like that. So I guess you would answer. I don't know how you'd give an answer with words, really.
Yeah.
I think. Do you have the one with solutions or without?
I mean, what is
This
the
one doesn't
that's-
have solution.
I think he might have just drawn it in.
So we draw it, we don't write it.
I don't know how you would describe it. If you have words to describe that, go ahead.
It shouldn't be so hard.
Can I see the question?
Direction.
Second one.
How do you want something harder?
And I mean, other stuff to ask on this is geometric problems, really. I assume you know geometry.
No, it's something entirely different.
Not on this. Okay, let's not do this. Okay.
You understand all that fun stuff that we were just thinking of? I have to know that.
Forces and torques. How is torque treating you?
Let's go over right hand rule stuff, because it depends on where your fingers go.
Okay. Right, so bars. Okay. We'll do torques now. Okay.
Just really quick.
Torque.
How do you torque? How do we do torque?
Is,
It's when you roll down the
it's
hill.
mu cross B,
Torque is mu cross B.
and mu is equal to current times acceleration.
Okay.
Not acceleration, the Lord area.
So I'm pretty sure.
Is it mu times I times A?
Okay, torque is usually we have a magnetic field B, and we have a loop inside the field that's going somewhere.
Which question is this?
Just a random question on torques.
Oh, it's rectangular.
And we have a current that's flowing in this direction.
Wait, what? Oh, this is just a random.
Yeah, just a random question. And so a rectangular loop of magnetic field that's going through it, that's enough to find the torque. Basically length.
Hey.
All this equal to. You okay there?
His head is not in this class right now.
Nice. W is equal to, so the width is 3 meters, the length is 4 meters, and we want to find the direction of the torque. And we want to find which orientation of the loop will give you the least energy, least potential energy.
You want the least potential to be 0
Yeah.
when,
Which orientation is going to be?
I'm totally messing so it's going to be, no?
Wait, what's the question?
Torque.
Potential, least potential, not 0. Least potential.
Okay, so it's going to be when it's like this.
You're looking
When
for
it's-
the least potential what right now?
Least potential energy.
So like
First, find the direction of it in this orientation, find the direction of the torque on it.
So
Let's start with that.
torque took with B.
B
What's torque?
Well, we first have to do A.
Torque is equal to mu cross B, right?
Right. So mu is IA.
Mu is equal to Ni.
I'm sorry.
So then you go, your fingers go in the direction of I, so your A is pointing out at you.
Right. So we
then
curl our
you're-
fingers in the direction of I. That's going to give you the direction of mu. Mu is pointing outside.
Mu is pointing outside.
So,
Yeah, is
Out
that
and
across
over.
B? I can't read.
yes, mu cross
Mu is pointing outside and
So
B is
then-
pointing to the right.
So then from
So
there,
it's-
your fingers go with B and they cross and they go into A.
Just mu cross B. So mu
No, you just
cross B.
Cross B, so
Do that.
it's
That's
so
the
towards
direction.
the up.
Yes.
Okay.
So that's the direction.
How'd you do it?
No, it's just I. Oh, just I.
NIA. How do you find mu?
What is in?
Mu, we curl our fingers in the direction of I. Our thumb gives you the direction of mu.
Okay.
Mu is pointing outside of the page, so outside of the loop. So it's in that direction, right?
Wait, but how do you know? No. What?
What if, huh?
I is
This is this I.
Oh, okay.
I is in that direction.
Yeah, but then how'd you do the torque? Because B is flowing, so torque is just out.
Mu, so sorry,
Yes.
torque is equal to mu cross B. Mu cross B. Mu cross B
Okay, so
gives you torque.
see, you make it harder than it needs to be.
No.
No.
It makes sense. This
Now it makes sense.
Okay.
direction.
So this is the direction of the torque. That means it's going to be spinning. So the torque points into the direction of the axis of rotation because of some scientists decided to define it like that. So it's going to be rotating like this, right?
Wait, alright.
Wait, is it going to go this direction? Yeah.
So, the torque we just found, is it rotating about that direction of the torque we found, or is it rotating into the direction we found?
If you have a wheel like that, and it's spinning like that, the direction of the torque is either here or here, depending on the way it's spinning.
Okay.
So the torque is always pointing along the axis of rotation. So since we just found that the torque points in this direction, so this is going to be the axis of rotation, right? So the loop is either going to rotate that way or this way.
That makes sense.
Now, we want to find the way that the loop rotates. How does it rotate? It always rotates to decrease its potential energy, right?
Decrease?
Decrease. We always want to decrease
So
potential
it's
energy.
going to go this way, or like,
So it's either going to go this way or this
yeah,
way.
that, no,
How does it go?
that way.
This way.
Yes.
Why?
The
Because
area, I'm sorry about that.
No, kind of right, like the
Mu
potential.
always wants to point in the direction of the B field.
Yes.
So mu is
Mu
pointing out.
always wants to point into the direction of mu. So since mu is in that direction, B is in that direction, wants to go that way, right? So the torque is going to make the loop go that way.
You can say that area wants to be in the direction of B as well, right? Because
Yes.
the area vector is going to.
Yes, but that means two things because
The area vector or the area?
Area vector.
Area you can't really say that because it's either this way or that way, right?
Okay.
But there's only one way that will decrease the potential,
Okay.
and that's when you have
Wait.
mu pointing towards.
So you're saying that it rotates around the torque axis?
It rotates around the axis that the torque is pointing towards.
Okay, so then how do you know which way?
And then it rotates towards the B field.
It's the way that so mu always wants to point into the direction of B. Mu is pointing outside, right? And B is pointing in that direction. So mu is going to try to point in that direction. That means the entire loop is going to rotate in that direction, like this.
Yeah.
If this was asked on a test and said what directions it go ahead and like counterclockwise.
Just start. You can say, I guess you can say counterclockwise looking from above. Stay creative.
Yeah.
Looking So from any other way.
If
If you look from any other way, how is it? If it's counterclockwise looking from above.
Yeah, because if you look from above, then it'd be clockwise.
So what is in the mu equals NIA? What's N?
N is the number of loops. We don't have any. We only have one loop.
So you just assume one.
They usually, if they don't tell you,
Yeah, it
it's
would be
probably
easy.
one. They don't tell you, unless it's obvious.
And I is current, and A is area.
And don't make this mistake. This is one loop. Don't make that mistake. When we say n, it means how many times.
We get it.
Okay.
Sorry.
So this is one loop. This is two loops. This is three loops. Okay. This is still one loop because the wire is only. Although it's two meshes, it's still one loop.
Okay.
Okay. So.
Don't worry.
So now we can find the direction of the torque. We found the torque. We found direction of the torque. We found magnitude. Potential energy.
Potential energy is
So
mu dot B.
Negative.
negative mu dot B.
Yeah.
Okay, so
Yeah.
okay, here's something to pay attention in this exams. Negative mu dot B is equal to mu B cosine theta.
Yeah.
It might give you a random theta, and half of you are going to use it to find
But that's
cosine
not
theta.
correct, right?
But that's not correct. Theta is always the angle between mu and B. It's always the angle between mu and B.
You're right, that makes sense.
In this case, it's going to be 90. Mu and B. Right? Right. Potential energy at this point is 0. But the minimum is not 0 in this system. The minimum is when mu points into the direction of B, which is negative.
So cosine of 180 would just be, or cosine of 0 would just be 1.
Cosine 0 is 1. And we have potential.
Cosine of 80, 180 would be negative 1.
So in our system, we're assuming that the highest potential is positive. That's when, if this is B, your area vector mu is pointing in this direction. This is B. That's the highest potential. Okay? That's unstable equilibrium. That means if you touch the loop like that, it's going to rotate that direction. But as long as you don't touch it, it's fine. As long as you don't.
That makes sense.
Zero potential energy is when mu is perpendicular to B. But 0 is not the least because we have negative. Negative potential energy is when B and mu
In the same direction.
This is the lowest possible potential energy.
Okay.
Of course, there's situations in between where it's like this, that's also negative. And when it's like that, that's also positive. I mean, those are the important ones. And this is the highest possible torque you can get. Right?
Which one?
This. This torque is sine theta is 90 in this situation. That's theta. This situation, theta is equal to 0. Here, theta is equal to 180.
And you were asking the original question.
Okay, so here, the torque is 0?
Torque?
No. When
Here? Yeah, torque is 0. Here also torque is 0. There are two kinds of equilibrium: stable equilibrium, unstable equilibrium. Stable equilibrium is when you have a ball on top of a hill. If you touch it, it falls down. Sorry, this is unstable equilibrium. Is when you have. Is there something funny?
No, I'm just trying to.
Try not to make.
I'm listening. I'm sorry.
Okay. Stable equilibrium. So unstable equilibrium is when you have a ball on top of a hill. Stable equilibrium is when you have a ball in between two hills. If you push it, it's going to come down. If you push this, it's going to come back. Okay? So if you push this, it's going to rotate into that direction. If you push this, it's going to stay like that. So try to push it. It's going to want to go back.
So the first example has the most amount of potential.
Energy, yes.
And it's like, what about the torque? It's just like
Zero torque.
zero torque on that first one?
Yes.
Okay. So then,
Because
Second
torque
one.
is what causes it to change. When you're saying equilibrium, that means it has no forces on it, no torques.
Yeah.
And this is also equilibrium, so no torques, no forces, nothing.
so no potential, no torque.
In this case, it's going to be somewhere.
it's going to be somewhere in
I guess
between.
It's different,
Yeah.
different here because it has to be highest torque. But
So the
Okay.
middle one is unstable and the top and bottom are stable? Is that what you're saying?
top and bottom are equilibrium. Top is unstable equilibrium. Bottom is stable equilibrium.
So the second one still has some potential, but it's just not as great as the first. The second one still has potential.
Potential, yes.
The
Potential
top-
energy.
The second one?
Potential energy.
Wait, they said it has 0%.
Potential energy is relative. There's no such thing as zero potential energy. It's always relative to the system definition. That's why we have zero. Zero is not the lowest one. We chose 0 to be negative because it's easier to make mu dot b. Okay.
Makes more sense.
Is there a problem on the exam that asks about this, or should we take one from the homework?
Not on this one.
There were ones in the homework that seemed kind of nice.
There's like a checkpoint. It's like about magnetic dipole moments. And then also has the like the largest magnetic torque.
Magnetic dipole moment. Is this, where is this? In the exam?
You can do that.
Starts at 8:30?
So R thing is 110 to 18.
Tomorrow I should just have
Well, if this is this one on the exam.
Let me just pull it up. This is a checkpoint question, or
Hey,
what's up?
where can you find these online? I'm so sorry. Like the live, no, I'm sorry, not the graduate exam, the live stream of this.
I send a link out with the email.
That's really nice. Look at me not thinking.
I'll probably be there.
So it's in the email that I send, and you can,
Wait, can you hear you or
Yeah,
just
you
watch
can.
you?
you should be able to hear me.
You can hear.
Well, it depends on how late I stay up. Because I want to stay up tonight because I know I don't want to stay up for the exam.
Okay, so on the exam, there's a question like this. Which orientation results in the largest magnetic potential energy of the dipole?
So it would be
A. Why A?
Hybrid cam balance.
So largest potential energy means it has the furthest to go, right?
Yeah.
So all of them want to rotate towards B. This is going to be the highest. This has the furthest to go.
Yeah.
Which one has the largest torque?
B.
E. Because the angle's 90.
Is there a question on torque? Yes, there is. A wire formed in the shape of a triangle AB.
Wait, why is B highest possible torque?
Sine of
Because torque is equal to mu cos B.
Okay, here's one.
Yeah,
Just goes on 90.
Yes. Sine 90.
Sine.
Okay, so this is the current I.
The one with most is B. So
What question is this one?
This is question 6 on the
Which one? It's one of the homework problems actually. But he changes up some stuff.
Yeah. So we have lengths. We have, let's call this W, let's call this L.
Alright, guys, I'll see you later.
And we have I is given. B is given. What is the direction of the area vector of the loop in position 1? This is position 1. This is position 2. What's the direction of the area vector?
Basil,
Yes,
do we have a review tomorrow?
at 8:30. Yeah.
Is that going to go as long too, or?
I doubt that.
the current is going down on the one.
So the direction is the current is going in this direction, so the mu is going outward.
So we just
Right? This is the direction it's going outward. What is the magnetic moment of the loop of current when in position 1? How much is it? Magnetic moment is new.
Yeah, so I.
Thanks, Basil.
No problem. And IA. So we have I, we have A. I suppose we know how to find I from length and width, right? I mean A. Right? A is equal to 1/2 times W times L. Area of a triangle. What is the torque on the loop in position 2? What's the torque on the loop in position 2? Magnetic field is still going outward.
torque is mu across B.
Mu across B. Where's mu?
Mu is into the base. page.
into the page.
And then,
E's out of the page.
so torque is 0.
Wait, what did you say for A? The area vector? Sorry, I missed that.
So the area vector, it's mu is equal to NIA, right? I is the current, A is the area vector. Area vector is
1/2 times.
1/2 times width times length.
Okay.
That's just the area of the
No,
triangle.
that's what?
No, like for the direction of the area vector?
Oh, direction?
Yeah. Okay.
Curl your fingers in the direction of the current and the thumb points towards you. What is the net change in magnetic potential energy between positions 1 and 2? Net change in potential energy.
So 2
It's going to be maximized.
Delta U. Presumably U2 minus
U, yeah. U2 minus U1.
Right.
And then that's
What's U2?
something dot
negative mu W.
Yeah, negative U dot B.
Between positions 1 and 2. I'm not sure if he means which one is 1. I mean, the magnitude of it, let's assume he wants the magnitude. Okay?
So it's 2 times either position 1 and 2.
Right, so it's going to be mu B cosine theta 1, or in our case theta 2, minus cosine theta 1. Sorry, this is magnitude. So cosine theta 1 and theta 2, one of them is 0, the other one is 180. So if theta is negative 1, the other is 1.
Yeah.
So this is going to be mu B times negative 2. Magnitude of that. So it's just going to be 2B.
2 mu B.
2 mu B. If he tells you that you start at position 1 and position 2, or you start at position 2 and go to position 1, then it matters which is which. One is going to be negative, one is going to be positive. It's always, delta is always after minus 4. Talking 13, I've never seen it this sounds.
It's okay.
I have a couple questions.
Yeah.
But if you want.
Okay. On this?
Yeah.
Okay.
So, unit 14, the wire and rectangular loop question. Wire and rectangular loop question.
In 13?
Yeah, this is 14.
14, yeah.
Yeah. No, wire and rectangular.
The wire, rectangular loop. Okay.
So, for number 3, it's 0. What is the reason for that? Is it because it's radial?
And because
Oh, it's very small. Okay, net force. Net force on created by the wire. See the x component on length. Oh, it's BC. Well,
Everything cancels out.
just all you have to know technically is that net force on a loop is always 0.
Okay.
On a closed loop is always 0.
yes. Okay.
But is that because of the right hand rule when you do stuff like
Well, no.
field
Or
or
no. F of x is not 0 in this situation. That's what we're talking about. It's when net force is 0 when you're inside a uniform magnetic field.
Yes.
Yes, we're not inside a uniform magnetic field. Because
I1 is
I mean, I1 is generating the magnetic field. That means the magnetic field here is going to be stronger than the magnetic field here.
yeah, true. Yeah.
Right? So there is going to be a net force on the loop, but it's only in the x direction. In the y direction, so the magnetic field is going into the board, right?
Yeah.
It is into the board here. The current is going this direction, right?
Mm-hmm.
So the force is going
Up. Yeah.
Sorry. It's going up I cross B, and C.
And then for the other one it's down.
The other one's down, but they're equal, right?
Yeah.
Because for every part of the wire here, there's another part here that has the exact same magnetic force on it. Although the force here is not the same as the force here, because it changes as a function of r.
But they cancel out because.
But this one cancels out this part cancels out this part,
Yeah.
etc., etc., etc. So they cancel out. That's why there's an net force. Sorry, go ahead.
So what about the other side, like BC and AD?
BC and AD, there should be a net force, shouldn't there? So, I think so. Yeah. So the magnetic field is going into the page. The current is going that direction. Current is going that direction.
So it's going to be.
Is the field?
To the right.
To the right. There's also going to be one here that's to the left,
But
right?
it's weaker.
But it's weaker
Okay.
because the magnetic field is smaller here than it is here. So the net force is in that direction. Okay. Yeah, that's a question from there. Why is there? Okay. Is there any questions on this part?
Yeah, I think he took the exact same problem, just put it on the practice test.
Oh, is it?
Yeah.
Okay, that's cool. Okay, is there any problem with magnetic torques? Torques, potential energies. Are you guys good with that? You can quiet. You can quiet.
I'm just taking it all in.
Okay. What's next? It's Ampere's law, right? Ampere's law, Weierstrass's law, right? Weierstrass's law. So questions on Weierstrass's law is either going to be two wires carrying current, and you want to find the force on one of them, or a wire carrying current, or a bunch of wires carrying current, and you want to find the magnetic force or field at some arbitrary point somewhere. So like the question we just did, we know how to find the forces on. So if they ask you, you have a wire that has I here, another infinite wire that has I in that direction, you want to find the magnetic field B at this point. There are infinite wires on side 1, this is side 2. You know how to do that? Yeah? How do you find the magnetic field from a wire?
B equals mu I equals
2 pi R or D.
Yeah.
This is going to be your R. 1 is going to be your R, 2. This is R1, right? They both point into the board in the same direction. That means we just add them together. Because when two vectors are pointing in the same direction, you add two vectors together. So B total is equal to B1 plus, or let's just do B total, plus mu naught I2 over 2 pi R2. And then we just simplify it. And the other part of it is like the question that we just did. It's just the what's L cross B? Where was magnetic forces on current? Which section was that? It's this section.
I think it's this section. It's like when you have the two wires next to each other, then you use.
That's a 4 torque. Shouldn't you do 4 torque?
Oh yeah, you're right actually.
Let's skip that.
It might have been the same section, just the forces and torques on currents.
Okay. Well, is there a problem with that though? Forces. If you have a wire that's carrying a certain current in any direction inside a magnetic field, in any way, you're just asked to find the force on a unit length of it. So on this segment L, length L, what's the force on it? You just say absolute equal to IL plus B.
Yeah.
Which is Again, I'm always taking the easiest way because I'm worried about concepts more than solving. This doesn't always, it's not always sine of 90, okay? So you can ask something like, this is B, and this is a wire that has a current I flowing through it and a length L. We're assuming we just want to find the force on this segment here, okay? And we want to find F, it's going to be IL. Remember, it's cross B, which is equal to. If you don't know the angle, look back to the original formula. If it's L across B, it's cross of two vectors. Cross of two vectors is always first vector. This is a constant. First vector, second vector, times the angle between the two vectors. This is the angle between L and B. The angle between L and B, so this angle theta. He might give you in the test, he might say, oh, this is theta, it's equal to, that's not 50, 150. And you simply find the theta that you want, the angle that you want. We'll call this alpha. We'll do sine of alpha. Don't just plug in blindly. If you have an equation, look at it. Look what each thing in the equation means. Okay. That's right. Ampere's law. And
Can you scroll up there?
yes. What else?
Ampere's law, motional EMF, or Faraday's law.
Faraday's law. Faraday's law is on.
Pretty good with most of the rest of it, actually.
Faraday's that's the last one. It's like
Did you
Yeah,
figure
Faraday's law.
So Ampere's law. Ampere's law tells you about the tells you how much magnetic field you have along a loop that has. Let's just write it first. B dot dl equal to mu naught I. Kind of looks like Gauss's law, doesn't it?
Yeah.
Right. Law was an enclosed surface. Here, this is just an enclosed path. Remember, Gauss's law was E dot dA, enclosed. dA, this is dl. So before a surface, now we would just take a line, a path. So if you have a bunch of currents, okay, so if you have a bunch of currents like that and you want to find the magnetic field at this point B, and you're asked to do it with Ampere's law. B dot dl is mu naught I. We take a path of C that for the same reasons we took a path symmetry using Gauss's equations problems. It's easier to simplify the integral. So this is your path. It's not a surface, it's just a path. If you integrate B dot dl along this path, it'll give you mu naught times I enclosed, times the sum of all the currents inside. Directional sum. So you're actually adding this current, and subtracting that current, then adding that current. And the current is going to be flowing inwards. Right? We're adding currents together. Current inside, you have one current here, another current there, another current there, right? So you can add these two, subtract that one, and then that current is going to move in that direction. Okay, so symmetric path, so we can simplify the integral to BL is equal to mu naught I equals. Solve for B L.
L is just 2 pi r.
L is 2 pi r. R is the distance from the center to
So in
your
that
path.
case, does it give you BO so R's law?
This is what that's all. So this is, they're probably going to tell you, oh, it's a distance D away from the center. Other stuff they can ask is, what's the magnetic field here? If they ask you for the magnetic field here, we take a path here, right? You do the same thing, B dot DL. But you use I enclosed only the current that's enclosed inside here, which is this current and this current. So if you have a shell as a current, what's the magnetic field inside here? 0. Why 0? Because if you take a path here, there's going to be 0 current enclosed inside.
That's if there's no like point charge or line charge in the center.
There's no what?
Like if there's no, so like on the big one
Yeah.
right there, you know into the screen, whereas there's nothing in the center, so that's why there's.
Yeah, there was nothing here, there wouldn't be any magnetic field.
Yeah.
And in this case, there's magnetic field here, but only from this
Mhm.
guy. So, I mean, the thing to ask about this is, again, something like this, but he'll ask you to find somewhere at this point. So we want to find B at this point. What we do is do the same thing. We take a path side, right? But the most challenging part about this is finding. That's easy. Do not I enclose. I enclose is the hardest part about this. How do you find I enclose?
It becomes squared minus a squared over r squared.
Yeah. So how do we think about it? Is the ratio of the cross-sectional area times the current. Why? We assume that the total current is distributed uniformly over the entire cross-sectional area. So if you have this thing that has current flowing through it, the current is distributed over the entire cross-sectional area. So like right outside is equal to right in the middle, everywhere has the same current flowing through it. This is the same thing. If we take I enclosed to be only the thing inside this area, let's call this A1. Let's call the total area big A. A1 over big A is going to be the same as a ratio of the currents, which is I enclosed over I total. So to find I enclosed, you just say it's a ratio of the areas, A1 over A, multiplied by I total. And the ratio of the areas is just going to be, like Aaron said, this is A, this is B, this is C. The smaller area is going to be the area of that circle minus the smaller circle, so it's going to be pi times B squared minus A squared over pi times C squared minus A squared. Because originally it was pi B squared, the area of this, minus pi A squared, smaller area. So how do we find that? We're just finding this area here. Right? The area of the bigger circle minus the area of the smaller circle leaves you with this. This is the same thing. And you end up with this equation. A squared minus B squared minus A squared, or C squared minus A squared. Times I total gives you the current that's enclosed inside your thing. First law. And he might ask you about weird ways to evaluate the integral of B dot DL. So I mean just weird integrals like the one he asked in class. Like and in the middle here you have a cylinder that has current coming out of there. And you want the integral of B dot DL from point P to point R to point S. So you want the integral of B dot DL.
Yeah.
Point P to point S through R. Through R. So you want the integral from P to R to S. B dot DL. How do we do this?
Well, P to R would be 0, 0.
P to R be 0.
Because it's gradient. And then R to S is its own. Well, they're 180, right? They're like.
Oh, well, I mean, even if it was 180, would it be 0?
I think so.
Like I think what we're both thinking of is so like in the homework example, it was like PRS, and so like RS was
So-
0 because.
If P was here, from here to here, yes, it would be 0.
Oh, you're saying if it's not 0 if it's like opposite each other. I thought 0 no matter what, as long as it's perpendicular to the circle. And then it just matters like the distance travels like not horizontally but along a circle, like the argument.
I see what you're saying.
So you just literally take the integral from R to S or P to S, depending on which way you want to do it.
Shouldn't come up to the 0.
Why? You're right about what the way you're thinking about. I see what you're thinking, but
What I'm thinking is that you take a path from here to here, that's 0. Integrate along this, that's not 0. From here to here, it's also 0. You go to here, it's not 0.
You could do that too.
Yes, but it's not going to give you 0 when you go from here to here.
Is it because it goes to the center?
It goes through the center, but what happens at the center? At the center, you have the same thing. It's just layers of circles that have the same.
Well, if you were to go through, you wouldn't necessarily go through 0. You just hit the surface of the thing. You go around it, and then you do the same thing. So it'd be.
Because yeah, because so
You wouldn't actually go through the center. You'd just be like the surface of the eye, and then you go around it just like you drew it, and then just do the same thing.
right, yeah. Well, yeah, that's one way to think about it. Yeah, but yeah, also because you switch. I mean, when you go from if assuming you want to go to the center, when you go from one place to the other, it's going to switch directions. Here, you do this because you're in the same direction.
Mm-hmm.
But when you go through the center, it switches directions. So it's going to go down. Because we switch directions here.
Okay. Well, yeah, that makes sense. So don't go through the center.
Don't go through the center.
Yeah, just don't go through the center.
That works.
So I'm going to give you the same question now. I don't know. I'll answer it. I'll think about this. Just don't go through the center for now.
Yeah. Okay.
Yeah, I'll think through this. But yeah, there's no, because this is the path you're taking, right?
Mm-hmm.
The magnetic field is in this direction here, in this direction here. Perpendicular 90 degrees, so this integral is going to give you 0. This integral is also going to give you 0. You're only going to have a value from here to here, plus from here to here. Right?
Yep.
So you can either find the length of this by whatever he gave you. He's probably going to give you something where you can figure out the length of it easily. He said something like this, just arbitrary points. And when you find the length, you can either actually integrate the thing. So if you integrate the thing, you're going to find b. Let's say b at distance, this is distance d. We're going to call this b at distance r. Oh no, it's just, I already have an r. B at a distance s, sure, there's an s. So b at distance d times the length of this path, L1, plus b at distance s, plus the length of path s. And that's just your integral. Instead of doing that, you can just apply Ampere's law and take the ratio of how much this path is to the total path.
So it'd be 1/2.
About 1/2.
Yeah.
Yes, in this case, it's about 1/2. I mean,
times
the points he gives you should indicate how much it is. If he asks you something else like this, he probably expects you to do with Ampere's law.
Okay.
Most of it.
Would you take off points if you went through?
Wait, so what would he exactly ask you, like?
Well, find the integral of b dot dl along this path from here to here, or from here to here.
Okay.
So
So kind of like the home problem.
Yeah.
exactly. Cool.
Or you can, I mean, if he says from P to R to S, it's straight out from P to S. It's the same thing.
Yeah.
I think you're expected to know that.
Yeah, because it only matters on the endpoints, right?
Yeah, so you can just do from here to here, and then here.
Yeah.
Instead of going that way. I mean, you should write down, oh, it's the same thing, and you know this because of this, and that. Okay. It's not First law. We just did that. Motional EMF. This is where you're moving a bar or changing flux. Did he ask any questions about motional EMF?
During
The
the exam.
No, practice exam don't have.
I think there was.
There is. So motional EMF is just an introduction to Faraday's law. Faraday's law is the general thing about induction. So because you remember how we started out with motional EMF, it was, oh, look at this. You have a bar that's moving at a velocity v through a magnetic field. It's everywhere. When you move this at velocity v, it's going to generate a charge separation. It's a force going to generate a current, blah, 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 okay? That's how we did it. When we introduced Faraday's law, we said change in flux is equal to EMF, right? No?
Yes.
Yes?
Yeah. Well, the equation.
Change in flux, EMF is equal to, well, this is just given by Lenz's law of the negative. So the EMF generated is just the change in flux over the change in time. When you change this, when you move this, you increase the area, therefore increase the flux, therefore induce an EMF. So all EMF questions can be solved with Faraday's law. Just a different way to think about it. Okay? Sometimes it may be easier to use one or the other. I mean, like, okay, another EMF question was when you had this loop. So this loop is just going like. That's into the page. That's really bad. That's into the page, and you have a magnetic field actually. Here's what it's going to look like. So this loop is like this. It's like A, B, and you have C and D. This is your axis, or this is your C, and this is your D, and this is your loop. And you have a magnetic field B going in that direction. Okay, and you don't have current. You don't have current yet, but you're going to move the loop. Okay, so you want to move the loop, and you're going to ask what is the current generated in the loop if you have a certain resistance. Okay, you with me?
Mm-hmm.
So we're trying to ask what's going to happen if you move the loop. What you can do is use motional EMF and say, okay, it has this bar moves at a velocity of v to wherever direction it's going to be. So it has two velocities, one in this direction, one in that direction. We don't worry about that one. It's going to have a direction v in here, direction v in here, right? This is going to generate an EMF that direction, whatever direction. L, it's going to be QV cross V, so we're moving in that direction. That's going to be charge separation. The outer one's going to be positive, the inner one's going to be negative. Same thing for here. You're going to have an EMF going in that direction. Or you can just do the EMF generating in the loop is just d phi by dt. D phi is equal to. You would usually not have to integrate phi. Phi is equal to the integral of d dot dA, right? The flux is the magnetic field that's going through an area, right? You would usually not have to integrate it because you would usually be working in a magnetic field that's uniform. So this would usually be, sure, you did have to integrate it though in one of the whiteboard problems, so you remember how to do that. Yeah? No? Okay, we'll go over something like that in a bit. So BA cosine theta. When you don't have to integrate. It's going to write when easy. When you don't have to integrate, just simplify to b cosine theta. So this is going to be b cosine theta.
Wait, so you have to integrate when it's not.
B is not uniform, yes.
Okay.
Usually when b is not uniform, you have to integrate.
Was it that problem where you have to take the integral and then the derivative of that?
Yeah. You didn't really have to take the derivative, but you can do it that way, yes. So it's going to be dA cosine theta dt. In this case, so one of them is always changing with respect to time. You can either change the magnetic field with respect to time and ask about flux, or the change of flux. You can either change the area, which is just moving that bar, changing the area with respect to time, or in this case, you're just changing the angle, right? So this is the angle A. This is the area vector A, and this is the magnetic field B. This is the angle between the two. Right? So BA cosine theta is the same as the rate of change of this angle. Sorry, you know what I mean. Rate of change, cosine the rate of change of this angle BA over dt. So to find the derivative of that, let's say they tell you omega is equal to 3 radians per second. That means theta is changing at a speed of 3 radians per second. That's omega.
Yeah. So
Right? Radian theta is grid.
yeah. So
Angle
theta,
frequency.
so yeah, theta equals omega times t.
Right. So we say d phi by dt, so that's going to be negative. B is a constant. No need to integrate. A, constant. Cosine, integral cosine sine, positive, theta, right?
Mm-hmm.
So it's going to be theta with respect to t. So omega theta is equal to set omega t. Omega t. Sine times omega. That's it. Dt. Omega, you have omega. You got this frequency. Was there something like this in the homework?
Yes.
Yes? Did you do it this way?
Yes.
Did we do it yet? You guys do it yet?
That was on 17.
I could go
But
on
unit 17. Which I still have to go first.
Yeah.
That's the one I remember.
To finish 16.
So one of them always changes in a question like this. And you just deal with the one that changes. Everything else is constant.
What's that say? W plus.
Omega.
So it's omega.
Omega t, and this is omega.
Theta just equals omega t.
So because this is theta is equal to omega t, so we write negative BA cosine omega t all dt. Finding the derivative of that with respect to time.
But that theta, which equals omega t, is in radians, so it's not like a theta in degrees. It's only radians. Yeah.
So we find the derivative of that with respect to time. It's just this. BA omega t sine, whatever. And he might ask you a question like, when is the flux maximum? When is the EMF maximum?
Or,
This is the EMF. Right? When is the EMF maximum? When is sine maximum? Sine is maximum when this is 90 degrees. When is the flux maximum? Flux is just this. Flux is maximum when theta is equal to 0. Magnitude. I'm saying magnitude wise.
Okay, yeah, okay.
Because one is direction.
Yeah,
and
yeah,
one is negative, one is positive.
Yeah.
And the EMF, I guess, is the same thing. This sign always bugged me. This sign, because it doesn't really tell you anything except, the only reason that sign is there is because of Lenz's law. Because Lenz's law tells you that the direction of the EMF is generated so that it opposes the change in flux. Remember that word?
Yeah.
So that's the only reason that sign is there. Actually, we'll do something on the direction of this thing that's generated. Okay, so when in this case, so this loop, if it moves in that direction, what's going to be the direction of the current generated in that loop?
Well, the angle's decreasing, so. Actually, the angle's increasing, right?
Is the flux increasing or decreasing?
What you're
Okay,
Flux is decreasing as you're going towards B, right?
If it
You're going
rotates
like
this
that,
way,
yeah.
it's going to increase.
Increase? Increase?
Yeah, it increases.
Flux
It
increases.
increases.
Oh, you said
No, I
decrease?
said decrease.
Okay, sorry. Yeah. Why does it increase?
Well, because as you rotate this way, A is turning this way, so the theta is increasing.
Okay, theta is increasing. Flux is given by cosine theta.
Yes.
Bigger thetas have smaller cosines. Right?
Well, it depends which way you're looking at the theta. Oh yeah.
Until 90. From 0 to 90. If you're increasing from 0 to 90, as theta goes from 0 to 90, cosine theta is decreasing. Forget about the angles. You don't have to analyze everything with equations. When you're moving this is loop, and that's the magnetic field. This has the highest area, magnetic field per area. When you're moving in that direction, the area that's perpendicular to the magnetic field is smaller.
Less, yeah.
When it's completely aligned with it, there's not a trading rate, right?
Or very minimal.
Or very minimal.
Yeah.
So we have 0. That means flux is decreasing, right? Flux is in this direction and decreasing. But the loop wants it to stay the same, right?
Yeah.
If it's decreasing, it wants it to stay the same, so it's going to generate a flux that goes, right, it's in this direction and decreasing, so it's going to generate a flux that goes in that direction. To generate a flux that's in that direction, you're going to have a current that goes like that.
So then essentially the current's going like this.
It's going from C to B.
Yeah.
From C to B, like this. This is drawn like that. Oh, this is a mess.
That makes sense.
Alright. Do you have any questions? Maybe.
Just do the matrix thing quick.
Yes.
Maybe I'll have more questions tomorrow.
What?
Yeah. No.
Yeah, I'll show you how.
Yeah. You want me to show one of them?
And
While you show another?
Do you need help with the thing?
Are we gonna need that matrices?
Maybe.
It would
Possibly.
help you for loops, like working tests.
So it could cause faults.
Oh, yeah.
If you have one of them.
I didn't.
You know how to do it?
Yeah.
No. Okay, so,
So here's the thing.
let's assume you have numbers. These are going to be numbers. Okay, so can you, look, open
Practice.
the bag, open my bag. Yes, here you're going to find your pen that you gave me last time.
Oh. I didn't remember.
So, these are numbers, right? These are actually going to be numbers, all of them. Numbers and numbers. Can I write it? Right?
Yeah, sure, go ahead.
So it's going to give you something like 1, 2, 5, 6, 7, 8. I give you numbers every one in your cases. Negative.
See you guys. See.
Yeah.
Good luck.
10, 11, 13. We're just trying to numbers. I1, I2, I3. Is it equal to, say, 0, 17, 13. Okay? So these numbers, right?
Okay.
We're trying to solve this. So you go to matrix. Okay, start over. Okay. Second matrix. Go to edit. This is the size of the matrix you want. We want a 3 by 4. 3 by 4. 1. Enter. Negative 1. 2. Yeah, negative 1. Yeah. 1. Flip them. And here you put this matrix, not these. You don't care about these. 0, 7, 8, 9, 17, 10, 11, 13. And now you exit. How do you exit? You go back to that thing. The matrix is already stored, so it's already stored. This is 3 by 4 matrix that we just entered. It should be stored. This is the math. These are the operations that you can do on matrices. This is row reduced echelon form. See you, Basil. I'll see you, man.
Thanks, man.
This is the first matrix. Select it. This tells me that I1 is equal to that, I2 is equal to that, I3 is equal to that.
pool. That would save us a lot of time.
Yeah.
How are we going to do that problem with RC stuff?
Probably.
I want to practice it.
Okay, this guy is here.
Chicken soup?
Is Dom still here? Dom, are you still there, Dom? Yes. Do you have any questions? No. Okay. Are you sure? It's your last chance. I never talked to a guy on China chat.
Dominic, you know.
Yeah, I know Dominic. That's thanks for the session, guys. No problem. Thanks for coming or watching.